Welcome to section 3.4, where we'll be discussing velocity and other rates of change. In part 1, we're going to be looking back at geometry a little bit and seeing how we can put calculus with geometry. It's a beautiful combination of maths. Let's just take a look at a circle and a cube real quick. If we note, as the radius of a circle increases in a linear fashion, meaning the radius goes from 1, 2, 3, 4, 5 at a certain rate, the area of that circle is going to expand as well, but not in a linear way. The area is going to get much larger much quicker, and then much smaller much quicker, just depending on how big our radius is and the rate of change of our radius. And that's kind of an interesting idea, is that as the radius grows larger in a linear fashion, the area is going to expand in a nonlinear fashion, in an exponential or some other type of fashion. The same idea can be said for three-dimensional shapes. If we were to increase the side length of the base here, or just a side length since they're all the same in a cube, as we increase that in a linear way, the volume of the cube is going to expand and increase in a different way. And so those rates of change that we're looking at, in this case geometric ones, are calculus, and they are derivatives. So we're going to be finding derivatives, aka rates of change, with geometric equations like area of a circle or volume of a cube, and we are going to see how they change. Now, in order to be successful in this section, we need to make sure that we understand how to just write out the functions here. So in number 1, we're dealing with the area of a circle, and we want to write that as a function of its radius r. All that means is that r is going to be the only variable that is in this function. Just like y equals 2x is y is a function of x, area is a function of the radius. As we know from geometry, the area of a circle is pi times r squared. And if you didn't remember that, you can Google it. So that is a way if you forget any of these. And now if we want to write this as a function using particular function notation, we can write it as a of r. It's up to you if you'd like to write it this way, but it is kind of the way that we write functions, right? Like f of x. And so this is saying that the area is defined solely in terms of r. R is the only variable in our equation here. Remember, pi is just a number, it's not a variable. So either one of these is appropriate. We have area of a circle A as a function of only its radius r. In part B, we want to get into the calculus. We want to find the rate of change, meaning take the derivative of our A function with respect to r. Now, instead of just writing a prime, what we're going to write is we're taking the derivative of a with respect to r, dA dr, just like we did dy dx, derivative of y with respect to x. In this case, our letters have just changed, that is all. And so what we're going to be doing is we're going to take the derivative of this function here that we've come up with and write it here. Now, really, we just have a number out front times r to the second. So what we're going to use is the power rule and bring this 2 out in front and multiply it by the pi, so it becomes 2 pi. And then r is raised to 1 less. And so there we have it. This is the rate of change of the area of the circle A with respect to its radius r. And again, this is totally fine way to write it. I just wanted to show you a different way of writing it as a function. They're both functions and they're both fine. Okay, in part C, what we want to do is evaluate the rate of change of A when r is 2 and when r is 6. So when r is 2, that means we want to evaluate the rate of change, meaning find what it is numerically, when r is 2. That means that we're going to be plugging in 2 for r. Now, the notation I used here is just, this is like a vertical line going down. This just means we're evaluating at whatever we write here, at r is 2. And I'll just keep working across, so I don't have a ton of room vertically. This becomes 2 times 2 pi, so 4 pi. And then when r is 6, it's the exact same idea. We're going to be finding or evaluating dA dr, the rate of change, at r equals 6. So that will give us 2 times pi times 6, or 12 pi. Now in math, we want to make sure that we have units to write after this, because what does this mean exactly? And part D is going to address that idea. So if R is measured in centimeters, then A would be measured in centimeters squared, or square centimeters. We want to know what the units of dA, dr are. So the numerator, dA, in all these cases, is the rate of change of the area, so that is in square centimeters, and the denominator, dr, is the change of the radius measured in centimeters. So we can write this as square centimeters per centimeter. This is a little bit confusing. It seems kind of strange, but remember that squared centimeters and centimeters are not like the same thing, right? A square centimeter is literally a unit of area. It's how much space this is taking up, a centimeter by a centimeter square, and a centimeter is like a more one-dimensional, and it is just a unit of length. So it's squared centimeters per centimeter. So we can write that in part C. So instead of just 4 pi, it's 4 pi square centimeters per centimeter. That line there also can mean per. And the same thing with 12 pi, I'm running out of room, but it's 12 pi, I'll write it here, squared centimeters per centimeter. Could you have also written centimeter squared? Yes, that is also fine. Here in number 2, we're again dealing with the area of a circle, but instead of writing it as a function of its radius r, we want to write it as a function of its as a function of its circumference, c. And so what I'm going to do is just start by writing what we know. We know that A is pi r squared, and that's A as a function of radius. We want it as a function of C, circumference. So let's deal with circumference off to the side and see what we can come up with. Circumference of a circle equals 2 pi times r. I take a look at the A formula and the C formula, or equations, and we see that they both have r in them. That's kind of their common denominator there. Therefore, I'm going to solve this circumference formula instead for r by dividing both sides by 2 pi. Then we can replace or substitute in what it equals. So we end up with r equals c over 2 pi when we rearrange that. That's helpful because we can then replace that in the original A formula, and therefore we won't have A in terms of r anymore. We'll have it in terms of our desired circumference, c. So in our next line, what we'll do is just replace r with what it equals, which is c over 2 pi. So we'll write that in there for r, and that's still squared. To square a fraction, we square the numerator and square the denominator. So we'll be left with c squared, and then 2 pi squared is 2 pi times 2 pi, which is 4 pi squared. Simplifying here, we can cancel this pi and one of those pi's, and then we're left with c squared, so I want to write A equals c squared over 4 pi. All right, to write this a little bit more simply, if you want, what we have up top there is fine, but this is really the number 1 over 4 pi. 1 over 4 pi is just the coefficient of our variable c squared, if that helps. So this one is fine, and this one is also fine. They mean the exact same thing. They're both area in terms of c. For part B, we want to find the rate of change of A with respect to C, which is dA dC, the rate of change of A with respect to C. What I'm going to do is take a look at this one here and see that this is just a number times c squared. C is the variable that we want to take with respect to. So that means that we're going to use the power rule with c. C is our variable. 1 over 4 pi is just a number. So that's going to stay out front. Using the power rule, we're going to bring the 2 out front. So it's 2 times 1 over 4 pi, which is 2 over 4 pi. And then c is raised to the first. We can simplify this. So dA dc is 1 over 2 pi times c, or c over 2 pi. They are both the same thing. So that is our derivative of a with respect to c. It's how our area is changing in terms of the circumference. For part C, we want to evaluate again at 2 different points. So we're first going to evaluate when c equals 1 pi, and then again when c equals 3 pi. So dA dc when c equals pi means plug in pi for c. So we'll have 1 over 2 pi times pi, and then our pi over our pi cancel, and we're left with 1/2. We'll get the units in just a moment. Then when c is 3 pi, we'll evaluate there. dA dc, the derivative of a with respect to c, when c equals 3 pi is 1 over 2 pi times 3 pi. Again, the pi's can cancel, and we're left with 3 over 2. Let's take a look at the units. We see that if c is measured in inches and if a is in square inches, what are the units of dA dc? Just like in the last example, a is the numerator, c is the denominator, therefore their rate of change is square inches per inch. So we'll write square inches or inches squared, square inches is fine. Square inches per inch, and the same thing with over here, square inches per inch. Example 3 is throwing in a fun shape that I wanted to use because I didn't want to use a cube. I thought that was too simple. But we're going to talk about the volume here of a square prism. It's kind of a weird shape that you don't hear about a lot. We hear rectangular prisms, triangular prisms. The way that a prism is named, like the name that's in front of it, is that's the shape of its base, and then the height is the distance between those two bases. So therefore, a square prism has a square base, and one up here too. It was not bad. And then we connect them. Not bad at all. So it has a square base, meaning that this is a square down here. And same with the top is also the same square. And then the base length is S. And then the height is double the base length, which means that the height is 2s. It's all still in terms of the same variable here. We don't want to introduce a new variable h because we know that we can call the height double s, 2s. Okay, now we want to write the volume of this. Well, the volume of any like cube or rectangular prism is just length times width times height, or base times length times height. It's just 3D. So the volume of this is going to be s times 2s. And of course we can simplify that. This would be 2s cubed. So that is our volume of our square prism as a function of s. For part B, we want to find the rate of change of the volume with respect to its base length s. So the rate of change of the volume, dV, with respect to s, ds. Again, we're going to use the power rule. These are not super difficult derivatives to take. We're going to bring the 3 out front and multiply it by the 2. So we'll have a 6 as our coefficient, and then s is raised to 1 less, so it's 6s squared. dV ds is 6s squared. For part C, we want to evaluate this rate of change of v. So evaluate dV ds when s is 5. So this is going to be 6 times 5 squared, which is 6 times 25, which is 150. Now this is a rate of change. The units would be the volume units divided by the S units, the base length. So I actually never said, I forgot to do that here. So let's just do this real quick. let's say that this is all in centimeters. Let's say that it's in centimeters. S is in centimeters. All right, so that means that the volume is cubic centimeters, and then S is centimeters. So cubic centimeters per centimeter is how our volume is changing when the base length is 5.